Welcome everybody to Industry 4.0 TV. My name is Kudzai Mandi Teresa, and today I'm out here in the beautiful town of Kempten in the south of Germany. And today I've got Melvin Francis, who's the project manager for OPC UA and TSN related services for a company called BE Services. So I'm going to let you introduce yourself.
Yeah. Thank you so much, Kudzai, for coming to our company. Welcome to Kempten, and I think you already started to like the city much, and it's like a pleasure for us to have you here because we have been following your podcast and also your YouTube videos and your LinkedIn posts. So they are really informative, and you spend a lot of time to create the content, and they are crisp and they are technically right, and also we are able to take a lot of information and learn from your podcast, and it's a great moment for us to have you here at our office, and I'm really happy that I'm contributing to your podcast and the YouTube channel as well.
Absolutely, thank you so much. So today we're going to be talking about OPC UA PubSub over TSN. Specifically, we're going to be delving into the research that BE Services is carrying out with respect to the application of OPC UA PubSub over TSN. So maybe Melvin, if you could clarify a bit about your work that you're doing around OPC UA PubSub over TSN.
Yeah, sure. So to quickly introduce about myself, I've been working in industrial automation for close to a decade. So right from my college internship, I've been working on industrial Ethernet. I've worked on protocols like openPOWERLINK, Profinet, EtherCAT, etc. And I was one of the developers of the openPOWERLINK stack, which is an open source stack, like it can be called as CAN over Ethernet. And in 2017, when all the buzzword like OPC over TSN started, I was one of the initial developers who started to work on this technology. I was one of the developers of Open62541, and I was responsible for integrating PubSub into the Open62541 stack along with TSN. So this was one of my work that we did in 2017, and we attended a lot of Plugfest. And right now at BE Services, I am managing the projects that are related to OPCA over TSN. And when we talk about OPCA, it's like machine to sensor to cloud communication. So I manage the projects that are M2M, more on the machine to machine communication, and that we are also having projects which are mainly into machine to cloud communications as well. So we have a team, and we are mostly, we can call ourselves as an OPCA company. So currently we are doing this research initiative project. It's a ZIM grant project which is funded by the German government. So we are working this project along with Offenburg University. So we have like 4 people from the university working and 2 people at BE Services working on this project, and currently we have attained a very good progress. It's a span of 2 years. 1 year is already completed, and today Kudzai is here to talk more about the project. Welcome, and let's explore more into the project.
Okay, so before we delve into the research project, I mean, as you might be aware, TSN is it's an old technology, but as far as industrial automation is concerned, it's relatively new, and a lot of it is still really under research. So a lot of people are not quite familiar with TSN or OPC PubSub over TSN. So maybe to kind of like set the foundation here, can you explain it like from the ground up? What is OPC UA PubSub over TSN, and maybe kind of like starting with TSN itself. What is TSN, and how do they kind of like combine then with OPC UA PubSub to kind of like set the foundation here?
Yeah. So let me explain what is the abbreviation of TSN is time sensitive networking. So when we talk about TSN, it's it's an old one, but it's a new technology for industrial automation. So TSN itself is it's a package of a group of standards creates TSN. So TSN, when we in the name itself, it says time. So when we are saying something as time sensitive networking, so imagine there are like V2 are there. So according to us now, our watch and your watch will have different times, right? Obviously it will be like at least 1 or 2 seconds or 3 seconds later, but we might see the minutes. It's now the time is like 11:07. Even you will show 11:07, but your seconds might be 15, and I might be leading, or you might be lagging, right? So this cannot happen in an industrial network, right? So the motors has to spin, for example, they have to spin in the right direction in a synchronized fashion. So they have to be in the accuracy of nanoseconds or in the sub-microsecond level. So when you are saying when they have to be in sub-microsecond level, you need some method of synchronizing, right? So when I say, Gudzai, like you're leading, so you have to slow down your clock. Then I need some protocol to say like when you and me are talking, we are friends, like so we can adjust in a very good manner. But imagine there are like 50 devices or more than 10 or 15 devices in a shop floor. So we need a specific strategy to adjust the time so that all the devices have the same timing and they are synchronized in the level of sub-microseconds. So what happens is this, so this is where you have this standard called as 802.1 AS. So this .1 AS standard gives us the provision like how the network clocks can be synchronized and using the PTP protocol. So this is like a protocol where we exchange sync packets and a series of packets, and we decide like, so imagine there are like 10 people in this room. So 10 people have their watches. Now our strategy is to have the watch time synchronized. So we decide like who's going to have the best clock, the clock with good accuracy, maybe the person with a good watch. So there will be like 6 parameters to say that the person with a good watch. So the person should have a very good watch. Maybe the crystal should be good. The clock priority should be good. So they have the 6 parameters in this algorithm. So this is called as BMCA algorithm. So best master clock algorithm. So once you decide who's the best master clock, and then we call them as the grandmaster and the other participants. So we have 10 participants. So we have decided on one grandmaster and the other participants are the slaves. So we have 9 slaves and 1 grandmaster. So what happens is this, each one talks to each other, each goes to the grandmaster and asks for the clock, and then the grandmaster gives you the clock. Now if you're leading, and then you adjust your time and then you come back, oh, you're leading now. And then you oscillate between adjust front and back, and then you are in sync with the grandmaster, and then you continuously exchange, say that you share your time, grandmaster says you're front or back, and then it returns back with the information, you adjust your clock, and then you're synchronized. So to visualize this, there is something called as 1 PPS signal. It's 1 pulse per second. So all the 10 people in the room are going to say, whenever it's 1 second, they are going to raise their hand. So similarly in the devices, we have one signal trigger that happens, and then if you look at the when you tap the signal on a digital oscilloscope, then you can see like when they are syncing, the pulses are oscillating, and then they come together each other in a single line, and the accuracy is in sub-microsecond level.
Okay, so maybe just to kind of like understand it a bit more here. So what you're saying is that using this 1 pulse per second mechanism is that every second a pulse is sent out to the master, right?
Yep.
And then the master will be able to determine by how much you're lagging, and then they send that information back to you to say correct your frequency or your time until everyone is in sync.
In sync. Okay. Yeah. Whatever you said is right, but only one change is it's the pulse per second is a debug feature, which tells you that they are all in the same thing, but the communication happens with the PTP protocol. The packets are sent on the network, and then they are, so for example, a sync message is sent, and then you get the delay request. There are a lot of parameters that are being calculated, which we can see in detail when we go into much more on the technical level. But the 1 PPS is for debug purpose, but really what happens is the exchange of PTP packets between the devices is what is helping us to adjust the clocks accordingly.
Okay, interesting. So that's the time aspect of it. So is it like the only parameter that is involved as far as TSN is concerned?
Yeah, so this is the most basic parameter. So once you have the device synchronized, so when .1 AS is done, now this device is time capable, it's time aware, it understands that every device is in the network is time aware, and then comes the next important technology, the next important standard is 802.1 QBV. So QBV says like, okay, now we are all in the same time. So for example, in the 10 people in the room, I'm going back to the example of 10 people in the room. So everybody is going to, there are 3 people in the room who's going to talk very important information. but the time available is just 1 minute. But everybody are just they are having chit chats in their items. But these three people, right? They need to have the importance of time in 1 minute. They need specific time, but we do not know what the other conversations like. Some people might joke, some people might gossip, but there is some important information coming in all the time. So what happens is we decide, like the group decides, these three people will get 40 seconds of time every minute. Every minute 40 seconds of time. These three people have to talk so that we do not miss the important information, and the rest of the 20 seconds the other chit chats, gossips and other unwanted information can be spoken. But the next minute again we get this 40 seconds of undivided, no other people can talk, all the people have their mouths locked. So the mouths can be compared to the gates in QBV, and the information that they are talking, right, the important information, gossips or jokes can be classified as traffic classes. So
Yeah, sure. Okay, so maybe just also again to try and understand it much better. So what we're saying here is that, to use your example, we've got 10 people in the room, right? And we've only got so much bandwidth, right? So we've got 1 minute, which is 60 seconds. But what we're saying is that we want to make sure that we allocate, we prioritize that time. So if like there's 3 people, we've got important stuff to say, we want to make sure that they are always allocated enough time such that their message is heard and never like misunderstood. So that 40 seconds is allocated to those 3 people. We never know when they are going to talk, but we make sure that whenever they decide to talk, they've got that time allocated for them. There's no, and then the other ones who are joking, gossiping, they just can kind of like share the other
available bandwidth. So here the viewers might have a question. So how do we know that this 40 seconds starts at 0 and ends at 40 and other people can talk? Can you answer this? Like, how do everybody knows that their time has started now?
Okay. Yes.
Can you answer it? Because they are already in time sync, right?
Yes.
So since they are all in time sync, they know that their time starts at 0 and ends at 40, and the other 7 people knows that their bandwidth starts at 40 and ends at 60, because they are all having the same clock, right? So they all be looking at the watch. Now my watch says 11:14 and it's 0 seconds. Now I'm going to talk the important information for next 40 seconds, and then once the 40 second ends, the other gossipers are looking at their clock to get their slot in, and then they will start doing it.
Okay, all right. Maybe you should kind of like bring it back home again. So maybe talking about like real industrial setting. So in this case, the 10 people, what would be those 10 people in an industrial
so
setting?
in industrial automation, we can say like, let us keep the grandmaster as a master device. And then the 3 other important people are the motor drives, X, Y, Z axis in a robotic arm maybe. So they are all there, and the other players, right? So you will also have traffic that are maybe diagnostics data. So you need to diagnose the data here, and there are configuration data to configure the network, and you might have audio video data. Maybe the audio video data can be compared to a CCTV footage that is available on the factory floor. So previously this was done on a separate IT network, and whatever we are doing here on the field level can be called as the OT network. TSN gives this capability to integrate both IT and OT network, because gossips have their own time, jokes have their own time, and the critical information, the motor control data, can have their own dedicated bandwidth, and all of them are time aware. So this will work in harmony. So this is the crux of TSN.
Okay, so it sounds like pretty much like the job that is being done by existing field bus protocols, right? To like kind of like achieve that deterministic time. So are we saying that TSN is meant to replace those field bus protocols?
TSN will not replace these field bus protocols. TSN enables them to do it. So for example, if I take openPOWERLINK, POWERLINK has this particular, just like the synchronization messages, like the PTP protocol, it has something called as SOC. It is called a start-off cycle. So the master will send this start-off cycle signal to all the slaves. So all the slaves will be ready. Hey, I'm going to receive the packet in next 2 microseconds. So I have to be ready with my resources ready. So when the packet startup cycle ready, so all of them, they will organize themselves accordingly. So this particular problem of having a special hardware, so for example, openPOWERLINK and Profinet can run at 5 ms cycle time or 1 ms cycle time. So when I say cycle time is sending one packet to all the slaves in the network. So it's easy, you can just use any hardware. But when you're going for sub millisecond, or when you're going into a cycle time of 250 microseconds or 100 microseconds or 50 microsecond cycle time, it will be very difficult. You need special hardware or special layer 2 and layer 1 for this to be achieved. But when you're replacing it with TSN, you have all the devices in the network are time aware and they know what's their bandwidth available, and you can. So TSN is just not with OPC. So TSN can work along with Profinet, TSN can work along with CC-Link, and there are many possibilities for this as well. So also EtherCAT as well, let me not miss that.
Okay, so are we saying in simple terms that you can have multiple field path protocols share the same?
So it is TSN is into layer 2 and layer 1. It's layer 2 protocol. It's nothing to do with what we are going to do with an application. So we have the network ready and it gives you the capability to build on top of it. So that's the good thing of TSN. So right now we have just spoke about two important stuff of TSN, that is 802.1 AS and 802.1 QBV, and we are yet to discuss QBR, QAV. There are a lot other more standards which enable us to achieve the requirements of the industrial Ethernet.
Okay, so now that we've got a basic understanding of what time-sensitive networking is, I would like to find out from you, where does OPC UA come into the picture?
Yep. The story is, so let me tell you my version of story about what has happened with OPC UA and in the industrial automation field. So previously we had multiple protocols. We had openPOWERLINK, we had EtherCAT, we had Ethernet IP, Profinet, all of them were there. So each one was backed up their own founders. So let me not, everybody is aware like who drives these technologies. So the problem is, imagine if a vendor buys a master device, a master controller from which is openPOWERLINK enabled, and then he buys a motor control drive from a different vendor which understands only Profinet. openPOWERLINK and Profinet cannot communicate with each other, right? So the machine builder is now in a problem where he cannot interoperable because the master controller has very good features, better than other vendors, so he chooses that. This drive has better features, so he chooses that. But just because they don't talk the same language, it's becoming a problem. So this has become a huge issue for the machine builders while building. They had to make sure that they are always locked to a single vendor. So even if one particular part is obsolete, they have to wait. You understand, right? So when you're locked to a vendor, there are many good things also are there, but you have a lot of limitations in the way you think and the way you are able to proceed. And also these field bus protocols cannot be easily communicated to the cloud. So this was another problem. So once you are communicated to the cloud, there are like endless possibilities. So once your device is IoT ready, then we call it as IIoT, right? Industrial Internet of Things. So this gives possibilities of a lot of new business models. So pay-per-use model, just in time. So you can call it like, there are like numerous possibilities that are also capable. And OPCA gives you this particular possibility where OPCA was already used in the industrial automation for a really long time. So where it gives you the possibility for the enterprise architecture to be integrated into the machine. So it was easy for them, but still OPCA was not capable to do the things that was being done by the legacy field bus protocols on the field level. So OPCA cannot, because it just had client server communications, right? So it was not capable to do the cycle time of 100 microseconds or 250 microseconds was not possible. It's literally not possible because client server is connection protocol. It's connection based protocol, so it is not possible. So then it was when they added the part 14 to the OPCA specification, which is the PubSub. It gave possibilities for us to send, publish and subscribe packets on the field level. but still publish and subscribe itself cannot be real time, right? You just prepare a UDP packet and then you with the OPC information model and then you put it on the network, but still you cannot guarantee the 100 microseconds or quick cycle time and the deterministic real time time critical like you're placing the packet every time on the network cannot be guaranteed, right? So that's when OPCA was already there, and then you add this part 14 specification PubSub, and along with this when you add TSN, this gives you M2M, which is machine to machine on the field level, and also machine to cloud, which is already established by OPCA. So this gives you an entire solution for industrial Ethernet.
Okay, all right, interesting. So now these two variants, as it were, of OPC UA PubSub, right? So the other one is OPC UA PubSub over brokered communication,
yeah. Mm-hmm.
And then there's also brokerless OPC UA PubSub. Mm-hmm. So in this instance, which specific version of OPC UA PubSub is TSN applicable?
Yeah, so it's a very good question. So when you're talking about IoT, where you have a small sensor and then it needs to ping the value every 1 second or every 500 ms, you will need OPCA publisher over MQTT. So you're sending it to the broker and the broker sends it to a different subscriber, and the subscriber can be your phone. So that is good for when you're going from machine to cloud and you want to send the data like 500 ms or 1 second, the publishing interval is low, it's fine. But when you're talking about sub millisecond, when you're coming into 500 microseconds, 250 microseconds, this cannot work, right? The broker cannot service to this level guaranteed. So this is that's when PubSub is coming to the brokerless world, and also there are multiple variants where PubSub over UDP is there, and also PubSub on raw Ethernet is there. So this is for quick packet preparation, and then you put it into the network and it just goes directly to the subscriber so that the real-time guarantee is done.
Okay, so maybe there's also something that I'm curious to find out here is I know there's efforts around OPC UA field level communication, what they call FLC. Right? So what's the relationship there? Is it like a standardization or on top of TSN, or what's the relationship?
Yeah, so OPC FLC clearly defines what needs to be, what OPCA PubSub should do on top of TSN. Yeah, your understanding is right. But yeah, it's just not, PubSub is just not a field level. So this is where our audience should might get confused, like, yeah, PubSub, yeah, I'm using publisher and subscriber model for sending the data to the cloud, but why the same broker can be used on the field level? So when you're going for high precision and critical systems, broker cannot service these kind of timing guarantees. So that's when we are going for the brokerless model.
Okay, so okay, now I think we've got that full understanding of what TSN is and what OPC UA over TSN is. So maybe now we need to kind of like get into the project, the research project that you're currently involved in. Can you maybe start by kind of like giving us an introduction into what are the objectives of the research?
So this research project was, so back in 2015, we were, BE Services was just working on, so we were providing integration services to Codesys. And so we were looking into other technologies which we want to explore. So that's when we found out that in 2018, when we started to propose this project for getting a grant, we decided that it should be OPCA and TSN, because right now we are very clear that what's the value OPCA plus TSN can create. But right now, if you see in the market, there are no ready-made stacks or SDKs that are available for a machine builder or any company that they want to take and they want to start creating and start building their application. It's not available already. So the main problems that we see is the stack is cumbersome. So when you are talking about OPCA TSN, it's just not OPCA TSN like two stacks. It's like you need a TCP IP stack, you need PTP stack, the software that orchestrates the TSN related items, you need a configuration stack, you need an RTOS, you need client, server, publisher, subscriber, and on top of it, you need to run your application. So we are talking about close to 6 to 7 stacks running independently as an orchestra, and all of them has to be fitting on a small ARM processor on a drive, right? So this is where the problem is, and our project is having the specific goal to reach to achieve ultra low footprint stack, which has all the aspects that I told, and it has to run on an ARM platform, and also we are targeting of both wired and the wireless part. So this is where our research is based on, and we have achieved certain results. So we are having a lot of partners already. So we are working with the hardware that is provided by Renesas, ADI, TI, and also we are in talks with TT Tech and lot other companies. So our aspect is this SDK can work. It is, first of all, we would say it is OS independent. It can work on bare metal. It can work on freeRtos, Micrium OS, VxWorks, Linux RT. It can work on all the related OS, and also it is hardware independent. So the same SDK can work on, we will be having reference designs on Texas Instruments, Analog Devices, NXP. So whoever are having hardware ready, our goal is to have this particular stack running on all these platforms.
Okay, so what are some of the challenges that you see around the implementation of OPC PubSub over TSN?
Yeah, so when we are talking about TSN, one of the important challenges that we are facing is the testing part. So when I say, we gave an easy example about the time having a watch, right? So even you can have the 1 PPS signal and you can see it on the oscilloscope, but still you need to make sure that this synchronization is available over a long period of time. So you need to take millions of samples of data to say that our system is working fine. So for this, right now the testing systems that are available in the market are very expensive. So the expensive stuff are okay for big players and who wants to create a lot of machines. But when it comes for small players, just like a company who wants to try out TSN, it becomes very difficult for them. So we are having one specific space in this project to develop test systems which are open source, which are easily can be repeated at our customer end, and it's like most of open source, and we are also basing it on Linux. So we are having right now test systems which would work on which would help us to measure .1AS, the jitter of a packet, and also QBV. So we are doing this kind of framework, which will also we are also planning to show a demo very soon in this video as well.
Okay, interesting. Well, speaking about demos, I think we've heard enough of the theoretical stuff. Maybe right now we can kind of like jump into the architecture and the demo so that you can see in practical what it is that Melvin here is talking about.
Yeah, so I think we should stop standing and take our seats and open our laptops.
Yeah, sure, absolutely.
Okay, so coming to the architecture of our project. So our project is, as I told you, we have OPC UA TSN over both wired and wireless space. So this is how we envision our architecture to be. So on the layer 1 and layer 2, we are seeing as Wi-Fi TSN and also the wired TSN. So this will be the TSN interface. So all the blue components that are mentioned here will be developed in our project. So the parts that you are seeing here, this will be done by the chip manufacturers themselves. So this will not be in the scope of our project, but the TSN interface that we are using will be talking to the Ethernet drivers and also the registers level, and we will be using the resources of their devices here. So coming to the top layers, we need, as we spoke about, is .1AS and QBV. So these are the two important parts that we are planning now. So this software stack will have the TSN clock. As I told you, the clock that we are going to use is the TSN clock, and the .1AS stack will use it, and it will start the interactions from here. So on the top layers, as we go above, we see the OPC UA publisher, subscriber, client server, and all the other stuff are being shown here. So this is our overall architecture. You can see here that this will be the OPC UA application layer, this will be the network layer, and this will be the RT network interface, which is the TSN layer. So this is how our project is planned, and you can see like we need to analyze. So the project scope started from identifying the hardware. So that's when we found out one of our important partners like Renesas, TI, ADI. So we wanted to base our software development to a hardware, and that's when we chose these vendors, and then we started to develop some more custom hardware for our developments, and then we chose the OPC UA stack. So as I told you, our target is to get things working on the Matricon Flex SDK stack. So right now we are also trying to get the stack as lean as possible, and we are working on it. And then synchronization and getting the TSN components working is our next topics, which we will see on the demo that is available. So as and when we are speaking, we are working on the Embedded World 2023 demo. So we will be having a slot at OACDL booth, and that demo is like right now it's ready on a tabletop, which we can look at it at my lab at the office. So this is the overall architecture. So do you have any questions?
So maybe quickly, if you could like scroll down on your architecture. So maybe something that you could clarify for me. I was under the impression that TSN is like for Ethernet.
Yeah.
It's an Ethernet standard. So is it a separate TSN standard also for Wi-Fi? How
no,
does it work?
the standard itself is the same, but only the transform medium is changing from wired to wireless. So the wired network offers more determinism, and the quality of service for Wi-Fi is obviously going to change. But with the invention, like with the progressions of 5G, we are thinking like this can be also reaching the synchronization levels of Ethernet as well. So in our project right now, whatever we are showing for the Embedded World demo would be so this is the project architecture that we are planning. So so you can see that we are having these layers. So as I told you, the layer 1 is hardware specific, where it is done by their chip vendors themselves, and then we have the RTOS layer. So right now in this project we are using freeRtos, and for OPC UA stack we are using the Open 62541 stack to start with. As I told you, we are still working on the Matricon stack for making it more lean. So we are still working on it. And in this demo, we have not yet worked on QBU yet, but 802.1 EAS and QBV is working already. So we will be seeing a 4-node network. So we have so this RTOS, we did not name it because we are having things working on multiple RTOS. So we have FreeRtos, we have Linux, and we have bare metal applications working as well. So when we see the demo, we will be showing the working of how the .1 AS is working and how QBV is working, and we can see how our test tools is able to take it up. So when in the earlier parts of the video, I said like we are looking at 6 or 7 stacks that are needed. So you can see LLDP, we need .1 AS, we need QBV, TCP/IP stack like LWIP, or any other proprietary TCP/IP stacks, and server, client, publisher, subscriber, and we need a config app to configure the end device. For example, the QBV, Windows, VLAN priorities. Like there are multiple things that we can do on the .1 AS stack, .1 AS configurations as well. And also OPC UA itself needs to be configured for the right information model. So there are like many topics. This config app itself is a huge topic that needs to be addressed. So this is what we are realizing, and this we want to give it as a software development kit, which is also a low footprint platform, and it's hardware independent and RTOS independent, so that it's like one package for people to get OPC UA over TSN working.
Okay, interesting. Well, so it seems to me that there's quite a few tool sets that need to actually be realized before we could start actually implementing this in a solution. So are you like in a position to kind of like give an estimate or talk about the timelines as far as when do you think you would have like all the stacks and all the tools required for like companies to start?
Yeah, so right now we are already having the beta releases ready, and we are already sharing our releases to our customers for them to evaluate up to what we have done. So it's not like a production ready solution, but still we want to get early stage feedback with what we are doing. So things are already ready, but for someone like who's interested to see the technology and who wants to explore, we have all the stuff that is needed for one person to start with Linux. Everything is open source, so you just need to buy a Intel i210 NIC card. So this Intel i210 NIC card, it's like just a PCIe slot NIC card which you can plug it onto any PC, like not a laptop but a PC, where you can plug it into your motherboard, and then the drivers are installed. Everything is pre-ready in the Linux world, so you can just start taking it and using it right away. So maybe in a half a day's time you can get your own OPC UA TSN stuff working along with the test tools as well.
Nice. So shall we see a demo?
Yeah, sure. We can start a demo where we can check like how all the things are working and how we are doing it. So this is our demo level. So these are like 4 devices that are available now. So this is the ADI TSN switch. So this will be the grandmaster. So the example of 10 people in the room. So we can correlate with that. So this is where the ADI TSN switch will act upon, and we have the Renesas which is running FreeRtos, and then we have Moxa device. So this is a switch and also a device. So Moxa has like they have given this device for us to develop both. They have the switch firmware running in already, but we are using it to test our end device capabilities on this. And this one is a Linux box running RT Preempt Linux. It has the RT patch, and then it uses it has i210 NIC card which is connected here. So all the blue wires that you're seeing here is running TSN. So all the other wires that are, so there's only one wire here, and we can also connect other wires for configuration purposes. So they are just for the network configuration reasons. So this is how the network is built upon. So I can show you a quick to explain the demo architecture that we are seeing. We can compare it directly with the ADI TSN switch. We have the Renesas board and we have the Linux box. So this is how our test setup is right now available. So you can see that the Renesas board is having the OPC UA server, publisher and subscriber running, and then it publishes to the ADI switch. And from the ADI switch, it goes to the Linux box, and the Linux box does the same. It subscribes the Renesas values, and then it takes the value and then it loops back the data and publishes back, which is received at the Renesas end. So this is how our demo works here, and we have 1 PPS signal from the Renesas board and the ADI available. So we can see how the signals are working. So currently, let me switch. So in this demo, we can see that right now the Renesas board is not yet switched on. So you can see that these LEDs are not blinking. So, but here the ADI board is ready and it is already communicating. So what I'm trying, I will do now is I will start the Renesas board. The Renesas board is switched on. You can see that the LED is blinking, and then if we see the 1 PPS signal, you can see that the signals are away here, and right now they are starting to communicate with each other with the PTP synchronization. Slowly you can see that this particular signal, the green one is the Renesas and the yellow is the ADI board, and then they communicate with each other, and then you can see that in no time they will come into synchronization soon. So yeah, this is the instance where right now they are on sync with each other. So they started to exchange the packets. So the status LED, the red color and yellow color LED shows that they are in sync with each other. And also even we have the Moxa device running, and the Linux box is running the Linux PTP, and we can see the status that port 0, port 1, port 2, port 4, all of them are in sync, and you can see that they are time aware and the other TSN parameters here. So we need to go into the Wireshark trace level, the network trace level, to see how they are exchanging the packets. Right now we don't have anything moving, so it's going to be more, the next part of the demo will be to see how the network traffic will be captured from the Linux box, and we are going to plot graphs and see how we can visualize these items.
Okay, so Melvin, thank you so much for taking us through the background of TSN, the applications of OPC UA PubSub over TSN, and also giving us a demo showing us the real application on using real devices. Now, for people out there who want to get started with implementing of this tech, what are the next steps?
Yeah, so as I told you already, we have implemented something on Linux box already, and anybody who has a Linux PC and if they can buy the Linux i210 NIC card, which is a cheap one, where you can buy it for 100 to 150 euros, and you can also order it on Amazon. So it's like quite accessible already. So I can share you the link, which you can post it on the description of this video, where they can click and they can go to our project page and then get the getting started guide from there, and they can start to implement already on Linux. So if somebody is looking for to implement on an ARM platform, then the things are not completely open source. So whoever is serious about it and they want to put it into their product line, then they can reach us out from our website, or they can reach us out through LinkedIn or whichever platform for them is easy. And then we can sign an NDA and we can start the process where we can share certain resources to them. They can repeat it at their table, get a feel about it, and they can move forward from there.
Okay, perfect. So again, thank you so much for having me here in your company. It was really great to spend the day here and have a chat about this.
Yeah, it was a pleasure. And also a quick summary. So we saw from we started from OPC UA, and we had a history about how TSN worked, and also we spoke about the research project and demo. So I think now our viewers would have got a view about how to start working about them. I think we should have, we will be more interested to have more series to have hands-on experience on how to do it on Linux, so that the quick start guide that is available on our website can be also put in your YouTube channel, and then people can start using it, and they will. It can be easy to start place from using it on a Linux and getting a feel about this stuff. So thank you so much for being here and spending your valuable time. And we had a lot of fun discussing both on screen and off the screen. It was fun, and please continue your good work. And all the best for your channel to grow big and your professional career as well.
Thank you so much.